In this video, I'm going to be showing you how to create this procedural movement system, and it should work for any character, particularly ones with multiple legs, so 4 legs, 6, 8 in this case. It probably won't work too well for a biped or a human, not so much, but this is a recreation of an older tutorial that I did for YouTube, which was the step-by-step spider procedural system. It's basically the same kind of process, but with things that I've learned since then, because that video's quite old now. It's quite easy to just swap this out from one character to another. You basically just switch the mesh, switch the list of legs that you're using, and that's about it. And for some of this video, you'll probably find that a lot of it is just tweaking values and messing around, so you're going to have to sit through some of that. But I didn't just want to show you the final values I used and just tell you some magic numbers, because that doesn't really show you the real process. That just shows you how a magician would do it. And I also left in some sections where I kind of did things a little bit wrong and then realized later and so on, just to show you how the debugging works or how you can identify the issues. And if you like the way this looks, but you have some issue with maybe how I do some of the math or how I don't have particularly clean scripting in controlrig, just leave it in the comments and I'll just delete it because I don't really care. So we're going to get started, and what we'll be doing is not using this version of the character. We'll be doing it on a blockout version, and you can download that for free down below. I think I'll also include this final version as well somewhere. That might be a paid one or something. I've not figured that out yet. But yeah, I would probably recommend maybe just watching through the video rather than following it step by step, but it's up to you. I think you'd probably learn more if you just watched it all and then try to do it for yourself, and then when you get stuck you can come back and refer to things rather than just doing exactly what I'm doing, because that won't really teach you as much. But I mean, feel free to do what you want. I'd like to see your results as well, so if you make anything with this system or apply it to a different character or anything like that, feel free to tell me about that, post it. I've got Discord and so on, wherever, tweet me, whatever. Yeah, so let's get to it. The first step that I like to do is just to get things moving, just so we can check for any issues. So any issues with the skeleton, the skinning, whatever. I use the blockout one because it's easier to identify any issues, because you can see specifically which bone's going wrong and you don't have to worry too much about, skinning issues and so on. So I'm going to right click on the skeletal mesh, go to create, controlrig, open that up. And the first thing I'm going to do is add a FullBodyIK node. So search for FullBodyIK. This is basically an IK solver, except rather than it being a single chain, like just one leg, it's a full body. So normal IK solvers, a 2-bone IK, basic IK node, would do 2 bones and solve for that. So like a human's leg, you get the thigh and the calf. Fabric does longer chains. This is basically that except for many chains at once, so it pulls things around to try and solve for the target's positions or whatever. Yeah, so I've got other videos covering that. So just connect that up to forward solve. Set the root to pelvis. And then what we want to do is add effectors. And effectors are the target points that a bone is going to try to reach. So we want 1 for the pelvis. And then we need 8 more, because believe it or not, spiders have 8 legs. So 1, 2, 3, 4, 5, 6, 7, 8. Who do we appreciate? So set the first one to pelvis as the bone. And you'll see, oh shit, it's fallen through the floor. Right, we don't want that. So just drag in the rig hierarchy tab on the left, pelvis, get bone, and that gets us the transform of the pelvis bone. And that's before we make any changes. So before this FullBodyIK node's even in effect. So it's just this position here. So we plug in this transform to the transform and everything's back to normal. And now the exciting process, we need to do this for every single leg. I should have done an ant instead, so there are only 6 bones, but so we're not actually setting the position or the target of this final bone in each leg. What I've done is added an extra bone at the bottom, which controls no mesh at all, and this is essentially a leaf bone, and we're going to be using that as a target so that we can specify where the end of this bone is rather than just where this bone, because this bone's position is actually here. So rather than using that as a target, we're using the end of the chain, which I've got these handy little bones added for each one of the legs. So we're just going to select each one of these. So click that one, leg 1 underscore L004, and then the same for the R, then leg 2, blah, blah, blah. You get the idea. So it's the bottom bone in all of these leg chains. And then what we can do is we can just drag all these in, do get bone, and we get this badly overlapping list of each one of those bones. And what we need to do is just plug one of these into each one of the effector atoms. But these effector atoms, we need to tell what bone that we're actually using. So this is the target position. So currently we're just getting the existing position. We need to tell this which bone we want to set towards this target transform. So to set each of these bone names, you can click on this, scroll through the list, or you can select something in here and you click this little use selected item or use item selected. So we're going to do basically select the bone that we're going to plug in. If you click this browse icon, the little magnifying glass, it selects it here. So we can click that browse, then click use selected item, and then plug the transform in. So browse, put it in, pop in the transform. I did it in a different order there just to keep things interesting. Browse, pop it in, transform. Browse, do the transform first this time. Ooh. So how have you all been? Leave a comment if you're bored. Right, so that's the last one. So we're telling it where all the bones should be, and we're just saying be in the position that you're already in before this FullBodyIK node was even connected. And so magically, look at the procedural animation we've accomplished. We've made no difference whatsoever. But now what we can do, let's just drop down this transform, and this is for the pelvis, and drop down the transform that it's plugged into. Let's plug these in manually. So we've got the rotation, translation, and the scale. Yeah, fuck the scale. Right. So it's back in position again. But now for the translation, let's just add a number to it. So I'll add -50. You can see his body goes down and all his legs stay stuck to the floor. You can type over numbers in, type in whatever you want, and you'll see him move around. A more interesting way, or a better way to test it as well, if you select the pelvis bone, right click, new element, new control, you'll get a new control. And what we can do is we can use this as a target point. And by the way, when you right click and do new control, it's whatever current position it's in. So because I did the minus whatever number I did, it's created it down here, but it's irrelevant for this. So then what we do is just we're dragging the control and do get control. So it's the same as we did for a bone, except it's this control point that we can actually drag around in the viewport. So let's just use this transform instead of the pelvis transform. And now we can just click on this control, move it around, and you'll see that the spider's moving. Well, his body's moving at least. And one thing you'll notice, okay, so I'll just put him somewhat in his default position. You can see there's these little connectors that are bones as well that connect the legs. If we go too far this way, you'll start to see that they disappear and they kind of go inside the body, just the way it's all connected up and stuff. But we can solve that. So to solve that, we want to go to the settings in the FullBodyIK node and do sub iterations. Set some value for this, so I'm going to do 30. And then we need to tell all of these to use chains. So I do have a full video on this, but basically chains will make it so it tries to solve the number of the chain depth. So let's say we set a chain depth of 3 on all of these. It'll try to solve for this bone, and this bone before using anything else. It will use the other things if it has to. So if it's out of range or something, it'll start tweaking the rest of the body. But it basically prioritizes the chain based on the chain depth. So for each one of the legs, so make sure you ignore the pelvis, I'm just going to tap 3 for the chain depth. And I can gradually see out the corner of my eye that it is fixing things. Okay, so now that we've got the chain depth on, this leg seems a bit out of place. Did I miss one? Okay, so one leg's acting a little bit strange, but maybe it's okay. I don't know. For some reason, this one looked like it was lower than it should be or something weird. But so now that we've got the chain depth, you can see that these like small connector bones are actually pretty much retaining their position. We can probably make it fail to do that if we go far enough like that. Then they start intersecting and going inside each other. But that's at some extreme position that we're not going to have him in, hopefully. But for all intents and purposes, that's fine. So it's worth just whatever character you're doing, just playing around with this, making sure that all the bones move as they should. You know, you don't have any skinning issues and so on. But yeah, so that's working. So now what we need to do is, also, when you compile, the control goes back to its default position. So I'm just going to set it somewhere around where it should be. And then you can right click on it. Sometimes you have to deselect and right click. Just do 0 offset. And that just makes it so that when you compile, the default is whatever position you've set it to. So now what we want to do is make him move and make his legs move. So here's a diagram of the spider. And as you can see, my photorealistic spider drawing skills have improved since the last video. When he moves, and we're going to say that he's moving in this direction. I can't see the fucking cursor. That's better. Okay, so he's moving forward. Assume that his legs aren't moving. So he's just a skeletal mesh that's static and moving forward. At some point, he's going to move forward so that this leg here is over here somewhere. And I can maybe procedurally animate him. So he's over here somewhere, right? So I'll just make a copy of that and put him here. So we've projected him to be here, let's say. Or let's say he actually is there. So this is the real position. This is where he was. If we had his leg locked in place, so it was locked to where it started from, his leg would be, you know, somewhat like that. Something, I don't know. His leg would be reaching behind. And I'll do that in a different colour. And that's something I've learned since the last video. You can actually change the colour. It's just a new technology. So his leg is something like this, trying to reach this point. I drew that so badly, I'll just do that again. So his leg's reaching behind. So this is where he is now, the darker one. And this is where he was. And his leg is locked in place, let's say. This position is quite far away from this position. So we want it to make a new movement. And you can think of this as a radius around the position that it's in, or was in, or locked in. And when it leaves that radius, we trigger a new leg movement. Or you could think of it as just take the current position, which is how I prefer to think about it and actually do it. And if the leg's outside of the radius around this leg, or this foot, so the current locked position is outside of this in world space, then we trigger a new leg update. And that's basically what we're going to do. So we're going to update the position that it's targeting when it leaves the range. And then we'll tell it to target a new position, which is in front of the character. And the reason that we use in front of the character rather than this position is because as soon as it lands, it's already late. It's already sort of halfway to leaving. But if we project it forward by half of the step, then we've got more time. You know, it sort of lands here and it's got the full length of the step rather than just half a step. Anyway, so that's basically what we're going to do. So to do this, we need to know that for the projection, we basically want to know his velocity. So we're going to calculate his velocity. And we're also going to lock all the feet in place. And I think I'll lock the feet in place first because that is easier to do. So in order to lock the feet or legs in place, we want to lock them relative to the world. So this is what I'm calling the world, the actual level of the game. We want it to be locked in place relative to the actual game level. So that is world space. You can think of the other one, which is in controlrig, as rig space, and that's what it's called. And that's just relative to the character. So you can think of it as like a coordinate system that's just around the character, where 0, 0, 0 is like directly underneath, below the center of the character. And that can move around in world space. So we can convert from a position that's in rig space, which is the coordinate system of the character, to world space, and we can convert back as well, using a to world node and a from world node. So what we need to do is we want to save these positions that we're locking the feet in as world space positions so that they're not relative to the character. So when the character actually moves in the game, those positions don't update, they don't change, they're not relative to the character, so they just stay locked in place. And to hold those positions, what we're going to do is make a variable. So go to the My Blueprint tab, create a new variable, set to transform. Right click on this little pill icon to switch it to an array, or you can click the drop down there and switch it to an array. I'm going to call this world locked transforms. And I've added world to the front so that we remember that this is in world space. because before we actually use anything that's in world space in something like the FullBodyIK node, this operates in rig space. So this just wants positions relative to all it cares about, which is the rig, so relative to the character. So whenever we use values that were world space values, we need to convert them from world using the from world node conveniently, so that they're in rig space, and then we plug the transforms in as we would. So we've got this world lock transforms, and I'm going to duplicate this, and I'm going to call it world target transforms. And this is the one that's going to hold the target position where the foot's going to move to. Now, these arrays are empty currently. What we're going to do is we're going to create one entry in each of these for each one of the feet. So to do that, we want to create 8 entries in each, but I'm not just going to manually add them because we're going to add more arrays. We're going to have different arrays, one for the start of the path time, so when the current time when the leg lifts off, the target landing time, and so on. We're going to keep adding different arrays. So add a new variable, and this one's going to be rig element key. And what this is a reference to elements in the rig, and then the word key on the end for some reason. So what we can do is we can populate this rig element key array with references to all of the foot bones. And now I'm regretting not naming them foot 1, foot 2, foot 3, but whatever, we'll deal with that. So I'm going to call this rig element key array foot references. And then again, it's just, I always use the word foot, it's legs, but yeah. So these are going to contain the last bone in each one of these leg chains, which is the sort of leaf bone at the end. So what we can do is we can just select all of these, the last ones in these chains. So I'm just control clicking on all of the 004 bones basically. Then if we drag that in, you can do create item array. So this just creates an item array of those things that you selected. And now go to the My Blueprint tab, and we'll drag in foot references and do set foot references. And drag in, well, connect the array output from this item array to set foot references. So that's just basically saving all of our foot references into that variable. And now we need to actually call this, and we're going to only do this once because the foot references, the number of feet doesn't change. We just call this once, so we'll just do this on construction. So it's the equivalent of construction event in Blueprint or begin play, whatever you want to think about. So just search for construction event, connect that to the set foot references node, compile, make sure you don't get any errors. And then what we're going to do is loop through all of these. So just go, well, actually drag in the foot references array, do get foot references for each. So this is looping through each individual item that's in this array, so all 8 of them, 0 to 7. So for each one of these, we want to populate this world lock transforms array. So we drag in that and do get, and do add to add a new entry because it's currently empty. Connect the execution path from here, not the completed, make sure it's from the top, so that's in the body of the loop. And let's just give it a sensible value to start with. So the element is the actual value going into that index at the array. And the index will just keep increasing. So the first time we try and add one, it'll be at index 0. The next time it'll be index 1. So the indexes will actually match the indexes from this, because this for loop is going through index 0, then it'll go to index 1 and so on. And each time we're just adding a new entry. So the elements in this will match the elements in this. So to give it a sensible value, what I'll do is drag out from element, and then we can do get transform. So that's getting the transform of the current foot bone that we've referenced here. And because this is world locked transforms, what we're going to do from the transform, rather than plugging it in directly, we'll drag out and do to world. Bang that in. Compile, save. Now we're going to do the same for world target transform. So I'll just go through this quicker. So we'll just get the array reference, add, and we can use the same value, so the targets can be defaulted to the same starting position as well for now. You don't strictly have to put default values in for these because we will be overwriting them or setting them later, but it's just handy to have some value there in case there's like a frame or a delay before the first movement or something, and you don't want the feet to all be in some crazy position. So we've saved those. Now we also need the 2 arrays for when the foot starts lifting and when it is trying to end, so when it's trying to land. So I'll make a new variable. This will be a float. Once again, make sure it's an array. I'll rename this to start path times duplicate end path times. And then we basically just want to do the same again where we get reference to that, add an end trait, and for this one, the element we can leave it 0, I think, and then we'll do that for the end path times as well. So if all's well and good, we should have 8 entries in all of these arrays. For the start path time, I think what I'll do is I'll leave that at 0, and for the end path, I'll put a value of 1, just so they're different, and we do get some blend just initially when the whole thing spawns and before we've actually set any of these values. There's one more array that I want to add, and in this FullBodyIK node, we're not actually going to be plugging in the current leg position because that will just makes things not move at all. We're going to be plugging in some blend between the world locked transform, world target transform, based on the time. So this will all be exchanged for what I'll call output transforms. So make a new variable, switch to transform. You can call it whatever you want, whatever makes sense to you, but I'm going to call it output transforms. So that'll be our blend. And as we did before, I'll add this earlier on because I want it to, I'm just going to once again put in some sensible value. So output transforms get add. And I think for the output transforms, I'm going to do this in rig space so that if the character moves and nothing's updating, the legs just come with the character if it's in some kind of transition or whatever. So I'll just plug from the get transform directly into this one rather than going through the to world node. So because I've not added world to this variable name, just remember that this is in rig space and we'll do the conversion when we need to. And you could just do this in world space and save yourself doing the conversion back, but if we're ever drawing things like we're drawing the output transforms and so on, the draw node, so if we do, for example, draw line, or you can do draw transform for debugging, these are in rig space, so the values want to be in rig space. So I tend to try to make things in rig space where possible, and then world space for things that are literally locked in the world or that need to not move. Anyway, so we've got our arrays in place. Now, I think what we'll do is, firstly, let's just swap out all of these for their equivalent from the output transforms. So we can just delete all these. So make sure you don't delete the pelvis one. Keep the pelvis control. So look, we've managed to make a squid. And I think that happened in the first version of this video. Get output transforms at index 0 for the first one. So these numbers aren't going to quite match up. So 1 is 0, but whatever. Then copy the at node. You can double click on the path if you need to, or just connect it like that. I'm going to double click on the path. So that goes to there. Set the index to 1. Plug that into 2. Duplicate. I'll just make as many as we need of these, so there should be 8. So just copy and paste all those. Go through the numbers 0, 1, 2, 3, 4, 5, 6, 7. Then make sure that it's connected to this output transforms array. I mixed it up by going backwards on the last one, just to keep you interested. So then we just want to connect up these, so make sure they're all connected. Okay, so now that we've got the FullBodyIK node set up, with all the output transforms being used, let's just select all of these nodes, and make sure you don't grab the forward solve in that. We right click, collapse to function. That just turns it all into a single function. Then compile, save before you do any renaming. Whilst testing for some of this, I had some issue where I had to just restart the editor because it was saying some fatal error with graph something, just some bug. So if you get that issue, just restart. So now under the functions drop down, we've got one called new function. I'm just going to rename this. And I'll call this set final leg IK. then compile and save. It's always handy to compile and save after you do renaming of variables, especially functions, well, variables and functions. So whenever we call this, it's setting whatever output transform is on all these legs, or basically trying to solve for those positions. So somewhere before this, before we call this, we want to calculate what those positions should be, or update them if we need to, or blend them between each other and so on. So that's what we'll be doing next. So in order to keep track of where the feet should be to do the blend, we need to know what the current time is so that we can save that. When the leg sets off, we save the current time as a start path time. And then we add some value to the current time. So let's say add 0.25 to it, to the current time, and plug that into the end path time. So it will take 0.2 seconds to reach its target. For that, we need some kind of timer. So I'm going to create a new function, which is called increase timer. We'll add a new variable, which is going to be a float, and make sure it's not an array. So I'll just right click on that to make sure it's not an array. I'm going to call this cycle time. Now, this is just going to increase at 1 second per second for now. And typically I'd call it rig time. So it's just, that's the variable name that I just decided to use. I call it cycle time if the time isn't necessarily mapped one-to-one with real world time. And in our case, we might speed up the timer. So when the character moves faster, we might increase the timer so that the legs move faster and they update faster and so on. I'm not 100% sure if we'll do that, but I'm calling it cycle time. And you can think of it as a cycle because it's going to be going through, like, some legs will move, like let's say 1 and 2 move, then 3 and 5 and 4, whatever order we do it in, and they'll repeat. So after 1 second, they'll all do it again. So it's kind of like a cycle, but it's the time, I don't know, figure it out. So drag in cycle time, do set cycle time, connect that in. All we do is we get cycle time, the current value, add, then right click, delta time. So that's the time since the last update, so it last ran controlrig basically. Plug that in. So now it just increases this at 1 second per second. And if you don't believe me, you can just add a print node afterwards. Make sure that's connected in. And we'll just print the cycle time. So do get print. And if we actually call this function, so go back to the main rig. So if you just go back to forward solve here, you can call increase timer function. And now you see it printing that's increasing at 1 second per second. So next time, just trust me on that. And we can delete this print node. So now we're increasing the timer, and we'll be using that current time to blend between our world lock transforms to the world target transform. Then when the value goes over the end path time, so basically the foot has landed, we're going to swap these two. So we kind of say that whatever the previous target was is now the locked position. And we don't really need to calculate the next target at that point. We only need to do it when the leg lifts, so we can just leave that as it is. So we'll do the logic for that. And in my courses, what I do is I tend to like build this up a little bit slower, but for the interest of time and trying not to make this video too long, I'm just kind of doing a few steps at once rather than just testing each individual one, but hopefully you can keep up with that. The first thing I'm going to do now is check whether or not the foot position, so the unmodified foot position as it's passed into controlrig, basically the base pose or the base animation, if the position of the foot is further away than some value, let's say 200 units, from its world locked transform. So we're going to compare the two. And remember, one's in world space, so we'll do a little conversion before we check. If it's greater than some value, then we'll trigger a new leg path, and we'll figure that out once we get to it. So I'll make a new function which will be called trigger legs. And we're going to loop through all of the feet. So I'll get the foot references array for each, and make sure that when you connect this, you connect that to the execution path, the return node has to go uncompleted, not in the body. This is a problem people seem to have a lot, where they connect the return node in the body and it's trying to return 8 times. That doesn't work. I think even in the engine now it blocks you from doing that. I think if I call it, so I'll just add this function in after increase timer. Yeah, we get an error now. So what you need to do is connect it to completed. So after it's done all the body, it then returns. I can't stress that enough. So what we want to check is the current position of the foot. So we get this element, so just do get transform from the current element, so the current foot. we've got this transform, we want to compare it to the world locked transform. So if you drag out from this new you can plug in an index. And as I say, the indexes for these and these should match. So we can just use the index from this array. We might be doing quite a bit in this function. So what I'm going to do is drag out from index and promote to a local variable. So that's just a variable that's only accessible within this function. So it's not messing things up in here, or, adding too many variables. It's just in local variable section just for this function. Only this function can reference it. So I'm going to rename this to footindex. And we want to use the footindex here. So we're getting the world lock transform at the current index relative to this foot. And we want to compare these two transforms to get the distance. But as I say, this is in world space, this is in rig space. Now, we could convert this to the world and compare them, or convert this to rig space and compare them. The way I'm going to do it is this to rig space so that we can draw a line without a conversion needed. So let's just do the whole transform. So just drag out from this and we'll do from world, which takes it from world space to rig space. And now we can compare these values. So we drop down the transform on each. We take this translation, or it doesn't matter the order, and search for distance between, in brackets, vector, and plug the translation from the current position, the current bond location, into that. So we get the distance between the two. And what I think I'll do is I'll draw a line between these so we can see it actually happening. So drag out and do draw line. A is going to be the locked position. B is going to be the current position. And this should just draw a line. And before we involve the distance, I'll just get this to work. So let's just put some thickness to the line. Let's say 4. So it should be drawing a red line. However, when you actually play, oops, I'm on the wrong level. Oh, well, actually, we need to set up the character, don't we? Can't forget that step. So I'm in the third person template. So if I go to the third person blueprints, third person character, select our mesh, we're going to switch that to the spider, proc spider blockout SKM. You can see he's at some weird angle. That's because we've got an animation blueprint. Just delete the animation blueprint and compile, and then he's back to normal. And you could change the scale of him if you want to, but I'm going to move the camera back because he's a bit big. He's a big lad. Now we need to create an animation blueprint. So the animation blueprint is the thing that's going to tell it to use controlrig during its sort of calculation of how it should animate. So to do that, we go to our character, which is the proc spider blockout. Right click, create anim blueprint. We open that up. Whatever we plug into this result is what the animation will do. So here, typically, you'd be putting animations in and connecting them and state machines and so on. We don't want to mess with that. So we just right click, search for controlrig. Connect that to the result. Select the controlrig. Controlrig class, we want to set the class that we've just been working on. So this proc spider blockout, blah, 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 controlrig. And now, even though nothing's visibly changed, it should be using our control rig that we've been creating. Now we just need to tell our third person character to actually use that. So once again, select the mesh. You've got animation mode should be use animation blueprint. Here we want to set our proc spider blockout SKM skeleton anim blueprint. So now he's using that. But you still won't see anything. So we're drawing this line. And we're calling the function, so it should be drawing lines somewhere. You're not going to see that yet. And the reason for that is you need to enable a few commands to visualize the debug drawing from controlrig. And I feel like they could condense this into one thing, but it seems to be two. So if you open the console with the tilde key and do a.animnode.controlrig.debug space 1, press enter, still nothing. You also now need to do controlrig.enable draw interface in game space 1. Now we're seeing all these fancy lines being drawn. So these lines are drawing from where the character spawned. So you can see that it's directly above this position. And we're never updating those. We're never updating those world transforms. So all we're doing is drawing a line from wherever the world transforms were when we set them originally to where the character is now. So when we move around, you can see that those positions are locked in the world. They're still staying there. They're not moving along with the character. So that's all well and good. So we can open up our controlrig again, trigger legs function. What I'm going to do is make it so that if the distance between these two is greater than, so just drag out to greater than, let's say 200 units, so it's 200 in the greater than. If that's the case, we're going to change the color of this draw line. So let's say for blue, just drag out from blue, and we're going to do if, which acts more like a select from Blueprint, so, but a selecting controlrig does something different. So just if. Plug in the result from this greater than, so that's a condition. So if it's greater than, then we'll say blue is 0, and the value, and it'll just be red as it was. Whereas if it's less than that, it'll be false, and it'll use this value instead for blue. So for this, I'm going to use a value of 1. So now we should see that we get a purpley line when it's in range, and a red line when it's out of range. I'm just going to fly down to near the ground, and I've also got it set to current camera location, so it spawns near to the ground. So you can see these lines are purple now, but if I move 200 units away, they should start to go red. So you can see the ones on the left are red because I twisted slightly, so those are slightly longer, and then if I go a bit further, the other ones go red. If I go back, if they weren't all twisted, you can see they go purple again. So we know that our distance check is working. So we could remove this draw line now, but I think I'll keep it there because in case something goes wrong, like for example our world lock transforms aren't in the place we expect them to be, we do want something to be drawn. I think maybe instead we can just draw the lock transform. That might make more sense. Yeah, fuck it. See that off. So you don't need the draw node or that if node. We might draw this. I'm not going to bother, actually. Whatever. Right. Drag out from the foot index after we set that and do branch. So this is just an if statement. If it's greater than this value, we're going to trigger a new leg path. But we also want to check something else. So one more thing we want to check. We want to say and. So it's greater than that. So the distance is greater. And it's not currently moving. So the way that we know that the leg's not currently in a transition from one place to another is if the end time has not yet happened. If the end time is in the future, that means that we've recently set a new path and it's on its way there. So drag in end path times and do at the current foot index. So just get a copy of that foot index node, plug that in. So if the current time, this is our cycle time, is greater than the end path time, that means that we're not in a movement at the moment. So the leg is planted at its last location. It's not trying to move. It's not currently in a move. And then we plug this into the and. So it has to satisfy both of these conditions. So it has to be the distance away and already landed and not moving. In that event, we want to trigger a new leg path. So I'll just add a comment. So press C to add comments. Trigger new path here. So on the true path, we'll be triggering the new leg path. So let's just do the logic for how it's sort of triggering the path. So the first thing we want to do, we want to tell it to start the movement now, like at this current time, according to our cycle time. So just drag in the start path times and do set at. Once again, just get your local variable, the foot index. Oh, don't do set, do get. Pop that in, plug that into true. And the value we want to set that to is the current time, so the cycle time. So now it knows that it's starting a path at this current time when we trigger it. We want to also set the end time, so it knows when it should land. So set at current index. And the value for this is going to be the cycle time plus some value. So I think I said 0.25 earlier, so we'll just use that for now. And then also what we need to do is we want to say that the new place that it's locked in, basically where it's setting off its path, is the last place that it targeted. So wherever it targeted last, and so it landed somewhere, it waited there for a little bit, then it got out of range. We want to say whatever that target was, that's now our start point. So that's now our world locked transform. So we get world locked transforms, and do set at current index, and we're going to set that to whatever the target transform was. So at, pop that in at the current index, and we could just use the same variable reference. Connect that into the execution path. So now we're saying that the locked place that we're starting the path from is where the last one left off. And now we also want to say where the next target is. And for now, I'm going to keep this really simple. So I'll just do this in here. We might make a function for this to predict the leg targets and do traces and so on. But for now, we're just going to get a reference to that, set at for the world target transforms at the current index. And the value that we're going to use is just going to be the current foot. So we're looping through the foot. So we've got a reference to the foot here. I could promote this to a variable. I'm not going to bother because we're going to delete this. I'm just going to drag this over. Get transform. So that's a transform of the foot position. We'll just get the translation and add a value to it. And this is in rig space, remember. This is the transform in rig space. So what I'm going to do is I'm going to add some value to the y-axis. And the y-axis is forward relative to the character. So if you look at these axes at the bottom left, you'll see the x, y, z. The y-axis is forward. So that's the direction the character's facing. So all I'm going to do is arbitrarily just add, let's say 200 units, because that was what we used to trigger the path. So we want to go 200 units forward now. So the total stride would be 400 units. Or the total distance that the foot is on the ground for is 400 units if it's moving forward. So we're going to just project the current foot position 400 units forward. Sorry, 200 units forward. So on this add node, on the y-axis, just put in 200. So it just adds 200 to whatever that position is. And then before we plug it into this, remember these are world space. We're going to do to world. And then just drop down element and we'll just use a translation. The rotation doesn't matter because these feet don't have rotations or anything. And as I say, we'll probably change this and do this in a separate function. So now we've got the world target transform. So that's where it's targeting to, the world lock transform set. I think this would be a smart place to actually draw some of these transforms. So after we set the world lock transform, I'll do a draw transform node. And this has to be in rig space. I'll just take this value from here that we're using. So this is plugged into this element. So this is what we're actually setting it to. Let's just take this value. I do to from world, sorry, and pop that in. So it should draw a box, give it some thickness, set the mode to box, and I'm going to do the same to draw these ones. So in this case, we've already got this to world node. Yeah, we can just skip the to world node because we want it the original position. So we just draw that position. And what you can do, I think, if you select the node, the draw transform node, and drop down draw settings, there's a value of lifetime, and that's how long it'll draw for. And because this trigger only happens once, or it should only happen once, it basically triggers when it goes out of range, and then the next time it runs through this, it won't be out of range. Or the end time hasn't happened yet. So either way, it's not going to come through this path. So what we're going to do is we're going to give it a lifetime on this. So we'll just give it 0.5 as a lifetime for these draw transforms, just so it draws it for half a second so we can actually see the thing. So what I'm expecting to happen now, if we compile, save and run it, is just as he goes out of range, so when those lines switch from purple to red, we'll see some boxes drawn in front of the character, no matter what direction he's looking in or moving in. So there you can see that it's working. It's sort of updating and setting these points in front of the character. So I'll draw these in different colors just so we can understand what's going on. So the locked position, I think locked I'll say is red, and then the target I'll say is green. So just do 0, 1, 0. So at any given moment, you can see that the red ones are behind and the green ones are in front, and that's where we'll be transitioning between. So the locked position in red towards the green. And now we don't actually need to do the calculation and to transition it. So all we'll be doing is modifying this output transforms to either be where the red ones are drawn, or where the green ones are drawn, or somewhere in between, and never anything else. So we go back to our rig graph. After trigger legs, let's just add a function here, which is going to be calculate outputs. Compile, save, go back to the rig, just drag that in, calculate outputs. Open that up. Once again, we need to loop through all of the feet. So foot references for each. Connect that. Completed. Goes to the return. And now we need to calculate the blend between the start point of the path and the end point based on the current time. So if we pull in our cycle time, we want to map this between a range of 0 to 1, which is either going to be the locked position to the target position, so an alpha between the two. And the way we're going to map it between those is related to the start and end time. So if this number is exactly equal to the start time, we'll be at the start of the path, and it'll just output 0, which will be the start of the path. If this cycle time is the exact same time as the end path, it'll be at the end. If it's any time after that, it will also be at the end, and it'll just stay locked at the end until a new path gets triggered. And then if it's halfway between the two, it'll be at 0.5. So the way we're going to do that is just drag out from this and do remap. So remap the value between the source minimum, source maximum towards the target minimum, target maximum. So the minimum is going to be the start path time. So we do at. Once again, I'm going to promote this to a local variable in case we need to reuse it, which we will. Foot index. So we at our current, oops, I promote the wrong thing. My bad. Promote the index. And then rename that foot index. And then we use our foot index. So this is the start time. So that's the minimum that this value, or that we care about in relation to this value. So we just plug that in as the minimum. Then we do the same for the maximum, but for using the end path time. So at the foot index, pop that into source maximum. And this maps to a value of 0 to 1. Then we click clamp because we don't want it to go, if this value outputs at 2, then we'll kind of be extrapolating the position rather than interpolating between the start and end. It'll start over predicting it and crazy stuff. So make sure you've got clamp ticked. Then what we want to use with this alpha that we've got is a blend between the world locked transform and the world target transform. So drag in world locked at foot index and world target at foot index. So we want to blend between these two. And there's a handy way to do this. Just drag out, do interpolate. Plug one into A, one into B. The order doesn't matter here. So world locked goes into A, world target goes into B, start, end. The result goes into T, so that's the time, blend between the two. And I'll just move all these down a little bit. And what I'll do first is I'll just draw the transform. So this transform that we've got, remember this is rig space. So from world, because these are world space transforms that we've blended between. Bang that in. I'll set it to a box. Give it some thickness. And we are calling the function, yeah. Okay. So now you can see that these little red, it's a bit confusing because it's red. I'll just switch that up. What color didn't I use? So I didn't use blue, so I'll just set it to blue. And I'll make it bigger boxes as well. So the bigger blue boxes, you'll see transition from one place to the new spot. And now all we need to do, I say all we need to do, there's more to do. What we need to do now is instead of just drawing this transform, we actually just tell it to output those transforms. So we get our output transforms array. We do set at current index. And we use this transform. And remember that these want to be not in world space. So we do it after our from world conversion. Bang that in as the element. Now the legs should be moving whenever it loses and goes out of the range. And sometimes I think they're kind of double triggering, like it's sort of lands just outside of the range and re-triggers. Like I'm looking at these front legs and I think they're kind of like not locking in place as much as they should and so on. We can fix all of that. You should have something working now, but hopefully it looks roughly like this. So to make things a little bit more clear what's going on, rather than the feet just sliding along the floor from one position to another, we'll just add some height to them so you can see they actually lifting. So I worded that weird. So you can see that they are actually lifting. I've been recording for too long. What we're going to do is each time the foot is transitioning like this, we're just going to tweak the output slightly. So we'll just add some height to it. Now this is not an ideal way to do it, especially if you're doing something like a human character. You'd want to do a more complex way to interpolate. I'm just going to map this value from 0 to 1 to some curve that we just add on to the height. So drag out from the remap and search for evaluate curve. So this will just take a value from 0 to 1, source minimum maximum, and output whatever these values are from 0 to whatever you set it to, or from whatever you set it to whatever you set it to. So it's just going to be 0 to, let's say, I don't know, 50 to lift the legs up 50 units at maximum. Now we want the end of the curve to end on the ground, so we don't want it to end there. So just select the end one, set the value to 0. Now right click somewhere, so there's actually a line here, and this is difficult, you can't zoom in and so on, you can't zoom in further than this. But there is a line between these two, and if you just right click somewhere on it and do add key, you can select it, and this is, controlling the curve. So I'll just put this to 0.5 and set it to a value of 1. And I'm just going to select all of these. So I've just held shift and select all these, right click, do auto just to make it a smooth curve. And after the interpolation, before the from world node, although actually no, I'll do it after the from world node, because I want it to be lifting in the Z, so up and down relative to the character. So if the character was on a wall or upside down or something, I'd still want the lift to come away from the wall, not in world space. So if you just imagine the character, typically we'd just be adding a Z height so the legs would be lifting up. But if the character was upside down like this, the Z value in world space would be going up and down. Instead, we want it rig space, so it'd be going up and down relative to the character. So after the from world, once we're back in rig space, just drop down from this, translation, add. Drop down B, and just plug this result into the Z value. Target maximum is 50, so the maximum this value will be is 50. And now we're just going to draw this position rather than the transform before we modified it. We'll just plug this into the translation, and definitely for this one. So this just gets the translation plugged into translation. So you can see that the legs all lifted briefly. Creepily, you might say. I'm going to change this 50 to 100 just so they lift up higher. Now what we should see is that when the legs are doing a transition, they should lift up in the air. Okay, so you can see it sometimes they're kind of triggering twice, and it kind of looks like the legs are bouncing. So let's just fix that for now. So in our trigger legs function, actually, calculate output, sorry. No, trigger legs. Trigger legs, right. Okay, so we're adding this value on to the current leg position. Let's, instead of adding 200, let's just add 100 to it. So the legs don't project as far forward. And as I say, we'll be replacing that and making it a bit more complex. And I think I'll increase the range before we trigger the new movement. So that's where we've got this greater than 200. Let's say greater than 400. Now the legs should stretch further before they trigger a new path. Okay, maybe too far. And they still seem to be doing this little double jump thing a lot of the time. So I think that's pointing to a mistake that we've made somewhere. So to help figure out what's actually going on, I'm just going to bring in our trusty draw line that we deleted. I'm going to draw the line from, okay, so it needs to be the rig space. So the locked transform to the current transform. And we should just be drawing a line between the two now. So that worked, but then it seems to do this little small one for some reason. Okay, so I think the problem here is we're using the lock transform and checking the distance from that, but we don't necessarily update that. We're using the target. So we're comparing against basically where it started its path rather than where it ended its path. So that was just a mistake on my end. Actually, I mean, I did it in that order intentionally, but yeah, it was an obvious mistake. So swap this so it's comparing with the target transform rather than the lock transform. This is basically the start path if it's currently in a path. So in regards to when we trigger the legs, this is actually pretty irrelevant. So we'll just use that instead. I could delete this and this. Now everything should be as expected, which it is. So you can see when it goes out of range, it triggers all of the legs to the new spot, and they transition and they lift up. So you can see that the legs are lifting. And if you get some out of distance before others, you'll get them out of phase, so they're not all moving at once. And now I think I can put the distance back as we had it. So I had it adding 100 units. I'll try 200 again. Actually, I'll do 300 and I'll set 300 on the greater than. So if it goes out of 300 units, it'll move and it'll move 300 units in front. I think that 300 might be too big. The legs are sort of getting too stretchy. I'll go back to our original 200 for both. And a lot of this is just going to be testing values and whatever works for your character and the style and such. But okay, so that looks more normal. Like the distance the legs are sticking to their position in the world seems about right to me. And that doesn't look too far off what we're going for. So the two main issues that we've got at the moment is because all of the feet have the same radius and they're all in their exact position that they want to be in when we start, when the character moves forwards, oh, don't leave your hat behind, it's a formal occasion. When the character moves forwards, they all leave that radius, or the distance always reaches the maximum at the exact same time. And what that does is it causes all of the legs to trigger at once, all to move to a new spot. So it will stay perfectly in sync. And if you just spawn and don't press anything or turn or anything, and you just move, the legs just stay in sync like that. So that's one problem. Another issue is that even though they stay in sync, well, even if you turn around the character and try and get the distances to, so one leg leaves before the other, like, you make it so that leg leaves because you kind of go in this direction or twist or something, they're all just kind of randomly out of sync. And that's how I had it in the previous video, where they were kind of just randomized and the sync was just, whatever happens, we're just adding random numbers to it. What we want is to make it so, I'll just see if I can make this in a diagram. So we've got another photorealistic spider. What we want to do is we want to trigger legs in sync. And the way this works with spiders is it's something like this. So these legs would trigger at once, all at the same time. And then these legs would trigger at once. And this is called an alternating tetrapod gait. And I did just want to show off my drawing skills, but I've actually got an image for you. So this B is what we're going to recreate. So we want it so that front left, second right, third left, fourth right, all trigger at once. And then all the others trigger at the next time. And what we'll do is we'll use our timer. So we've got our, whatever we call it, cycle time or cycle rig, I think it was. We've got that. Whenever it goes to, let's say, a 0 or a whole number, so a 0 offset from whatever whole number it's at, we'll trigger some of the legs. So 4 of them. So L1, R2, L3, R4. I can't see the cursor. That's why I'm struggling to point things. So when it reaches the whole number, we trigger these ones. When it passes the halfway point, so it could be 0.5, 1.5, 10.5, whatever the number is, then we trigger all of these legs. But we keep in our distance check as kind of a catch-all, you know, just in case one leg goes out of range, even if it's not ready to be triggered again. And we just, you know, that leg will be out of sync and not right, but by the next time it comes around, it should resync and so on. So to do that, we just need to monitor our cycle time that just increases. So you can think of that as just a timeline that's increasing. Every time it crosses a whole number, we're going to trigger specific legs, and then whenever it crosses the halfway point, we'll trigger the other legs, and then we'll leave our distance thing intact. So let's just evaluate where we are at the starting point, just so we know that we've fixed the issue. If I spawn near to the ground and just hold forward, all the legs just hop in sync. They only become out of sync if I start doing some twisty stuff. So let's get to work. So before we do the trigger legs is doing it based on distance. So that's going to be our fallback. If the legs get too far away, we'll just say whatever, you know, no matter what, just trigger that leg. We shouldn't be using that too often. Hopefully our way of triggering the 4 legs, whichever ones they are, should prevent that for the most part. But like I say, there might be a case where it's walking over weird terrain and one of the legs gets stuck in quite a weird spot before it gets triggered and so on. So we just want to make sure that we do have this distance check. And we could probably change the values that it uses so it's a bit of a higher range because it's only a fallback and it's not the intended thing, but we can get to that. So firstly, let's just make something that prints true, then false, and true, then false. And what we'll be using that for is, if it's true, it'll be one set of legs, and if it's false, it'll be the other set of legs. And I'll figure out which legs it should be. I kind of forgot. But so make a new function, and this will be called force leg moves. That'll do. Right, so we have our cycle time, which just continually increases. Let's just duplicate that, and we're going to call this last forced leg move. And that's going to keep track of the time that the last time that we triggered a set of legs or a grouping of legs. So let's drag in our last forced leg move float value and our cycle time, and we'll put our cycle time above it. So if the cycle time is greater than the last forced leg move time plus some time offset. So I was doing 0.5 when I was explaining it earlier, but let's just do it a bit quicker than that. So we'll do 0.25. So if 0.25 has passed since we last triggered a set of legs, then we trigger the next set of legs and so on. So if it's greater than that, we need a branch. And the return is on completed for now. That should be fine. So if it's greater than that, we want to keep track of whether it's triggered set 1 or set 2. And because there's only 2 in my case, if you're doing something else where you need multiple sets, you might just approach this slightly differently. But because there's only 2, I'm just going to use a bool. So just create a new variable, which is a boolean. And I'll call this group 1 move. Oh, you can't do question marks in this. Okay. I tend to do bools with a question mark at the end just so I remember that it's kind of like, yeah, whatever. Group 1 move. Again, not the best name, but so if the current time is greater than the last forced leg move plus 0.25, then we want to just invert this. So just do set group 1 move. This is on the true path to whatever it is currently inverted. So just do not. So not whatever it is now, meaning it just flips. So it should go true, false, true, false. And then after this, we need to set the last forced leg move time to say we've just set one. So the next time it runs around, it doesn't just keep triggering it. So we just tell it that it's the cycle time. So this should go up the true path every 0.25 seconds. So let's just do a print to test that. So what I'm going to print is the group 1 move variable. Make sure you plug that into the value, not the enabled. I do that mistake nearly every time. I didn't do that time, luckily. So it should be printing true, false now. We just need to actually call our function. So force leg moves after increased timer, but before trigger legs. So you should see top left, true, false, true, false, true, false. I don't know how well that'll come through on the recording, but you should trust me that that's what it is. If you need to see things for longer, you can just select the node and change screen duration so it lasts longer. You can see it up here as well. True, false, true, false, true, false. Okay, cool. Now what we want to do is actually in this function, when we're doing the force leg move, is to actually trigger those legs. And we already have a function to trigger legs, but this is doing it based on, well, it's a messy thing, but it's doing it based on the distance between the previous target, so the previous landing spot, and where the leg is currently. We want it to be able to just force it to be specific indexes. So the way I'm going to do that is I'm going to pass in, well, firstly, I'll add a boolean, so on inputs, a new bool, and this will be called forced trigger. So we know that we're actually, we're basically using this function for two things. We've got the distance version, and then if this forced trigger is true, we're going to do some alternate condition which allows it to trigger this leg. So we keep all this the same. This is all just triggering the leg. And we don't have to duplicate the code, because if we change things, which we likely will do, we don't have to do that twice. And this whole section could be its own function. I'm not going to bother with that, but feel free to collapse it to a function if you want to. So we've got the force trigger, and we need to tell it which legs to trigger based on some indexes. So we're going to pass it 4 indexes. So the first group will be, let's say we pass it 0, 3, 6, I think, or whatever it'll be. I think I missed one then, but whatever. So on the inputs, just add a new integer array. I'll call it legs to trigger. We're going to just basically add into this condition. So this condition is checking that the distance is greater than, and that the leg's actually stationary at the moment. What we'll do is, instead of just having it check for that, we'll say alternately you can check if the current index is actually in this legs to trigger. If it is, then just carry on anyway, and we still trigger it, even if the distance is, not reached that maximum. So we do this, which combines these two, then we drag out and do OR, and then plug the result into the condition. So it's either all of this is true, oopsie daisy, all of this is true, or our legs to trigger. So when you plug things into a function, you can just right click anywhere and do legs to trigger, and it'll have it under a section called input arguments. So you don't have to drag paths or promote to local variables or anything. So get legs to trigger, and then do find, and the index we want to find is our current foot index. So if the current foot that we're looping through exists in that array that we've passed through, then we do want to trigger the current leg that we're on because it's in that array. So you can just plug the success into this, into B. So if it exists in the array, and we might want to also combine it with this just to make sure the leg's actually moving before we trigger it again. We don't want to trigger it whilst, if we triggered it while it's halfway, it'd probably, because we're updating the target, the world locked location, the target, it would be in its path, and then it'd kind of snap somewhere and then start over sort of thing. So we don't want that. So what I'll do is I mean, there is a better way to do this. I can do this. This can always be tricky. What I'm going to do is I'm just going to do it like a simple way. So I'll just do and here. So that goes into, I'll just do it into B, doesn't really matter. And then I'll plug this into there as well. There is a saner way to do this, but for the interest of time, I'm just going to do it like that. So if it's in the thing and the leg's not moving, or the distance is greater and it's not moving, then we trigger the legs. And one extra thing, we want to make sure that this force trigger is true, because otherwise it'll be, I don't know, that probably shouldn't actually matter, but I'm just going to do it anyway. So if it's in the legs to trigger array and right click, forced trigger is true from the input arguments, then we trigger the leg. So now if we go to force leg moves, we can call that function trigger legs, And this function basically gets called twice. So it gets called here in this force leg moves. But because we did it before the actual trigger legs that's in the main forward solve, it will trigger the legs before it gets to here. So all the legs will actually be moving. So our moving check will prevent it from trying to trigger it again or anything weird like that. So we want to take force trigger, so it actually uses our array. Then we can drag out from this and do make. So make array. Then any values we put in any values we put in here, it'll trigger those legs. So currently it just keeps triggering 0. So we want 4. Well, actually, we're going to switch between whether it's group 1 or group, well, you know, group 1 or group 0, group 1 or group 2, whichever way you want to think about it. So whether this is true or false, we're going to switch between either this or a different version. So the first set of legs I'll do is, if you remember, it's sort of like drawing a square. So it's like that to that to that to that. So we want index 0, skip 1, 2, then index 3. So we want 0, 3, 4, skip 5, skip 6, and then 7. So 0, 1, 2, 3, 4, 5, and then 7. A lot more challenging than it should have been. So you can see that all those legs are dancing, because they're moving no matter what. Because, you know, we're not checking they actually need to move the distance that they have to travel or anything. We're just constantly setting it, forcing those legs to move every 0.25 seconds. And also, we're just arbitrarily adding 200 units from the start point. So they're always just, you know, reaching forward every time. We'll get to all that. So it's either this one or the alternate. So just all the other numbers. So that would be, well, you can just guess it from here. So it would be 1. I'm just going to stop it doing that because it makes it more difficult. So we skip that. We've already done that. So we want 1, 2, 5, and 6. So 1, 2. Wait, no, we've already got 5. Wait. 1, 2. 6. What the hell? 1, 2. Okay, so I think we do 3 there. So yeah, so 1, 2, 3, then 6. I mean, I could have just looked at these numbers and the ones that we don't have, basically. So we want to swap between these two. So just drag out from legs to trigger and do if. So plug one of them into true, one into false. Doesn't really matter the order. And we just want to base it on this group 1 move variable. So it should now, once I connect this up, toggle between the two. So you can see that they're hopping out of sync. And let's just test that in the game. So you can see whilst it's walking, it looks pretty good. If he's just walking straight forwards. If we stop, it all goes a bit wild. Because we're not including the velocity or anything like that for the prediction, so that's not going to be great. But you can see that they're sort of triggering how they should be, I believe. I think I've messed it up, to be honest with you. One, no, 0. This should be 0, 3. 4 and 7. So that means this other one is 1, 2, 5, 6. I think that's what we want. I wondered what was going on there. I didn't connect it back together. There we go. Okay, that's what it should be like. And you can see if we're doing like weird moves, it is re-triggering legs that it doesn't necessarily want to move, but then they still end up going back into sync. So that's all good. It's just that it's always just projecting forward by the same amount. So we'll fix that next. So in order to make it so that the legs trigger and have a reasonable distance on them, we want to know the velocity of the character. So how fast the character is moving. Now, typically the way I do this is I calculate the velocity in controlrig. That's a little bit math heavy, and I'm not going to go through that. There is a simpler way, which is fine. It's just, I prefer calculating in here because if you just pass it in from the character, if you're not using a character, I don't think you've got access to the same velocity value from, like, we're just going to pass it through the animation blueprint. We're just going to get the character, pass it in. I'm not sure if that would work if you just use the controlrig directly in sequencer. You'd have to have a blueprint attached to it and so on. And also, typically the velocity z is zeroed out if you're on the ground. So if the character's on the ground, the velocity z is not calculating. And sometimes I want to use the z velocity, but in this case, we should be fine. I go through the other way in my courses, but for now, we're just going to do this the simple way. If you ask in the comments if you care about how to calculate the velocity, I'll tell you that. Right, so we go to our animation blueprint. And what we want to do is just pass in the velocity here, the character's velocity. So back to controlrig, we're just going to create a new variable, which is going to be called input velocity. That's a vector. And then select the variable after compiling and tick instance editable. And then if we go to our controlrig class in the animation blueprint, you've got this input section where controls show up, as well as any of these editable variables. So I'm just going to tick use pin for input velocity. And by the way, the output, I have no idea what that's for. It seems to just not work. Anytime you tick an input, it adds it as an output, but there's no actual output there, so you can't do anything with the value. I don't know. Don't know what that's supposed to be. So we need to set this input to something. So I'm just going to right click on this, binding, try get pawn owner, and we want the get velocity. Then compile, and then controlrig should have access to the velocity. So just to test that on forward solve, I do print input velocity. So it's 0 obviously in here because this isn't even using the animation blueprint, so it's not passing anything in. There, so you can see that the x and the y value are changing based on the velocity. And this is in world space. So you'll notice if I walk down the x-axis, down the y-axis, the number is pretty much 0 for x. And the y value is at the walk speed, which is approximately 600. Well, the walk speed is 600, but it was showing like 599 or something. So that's in world space, just keep that in mind. So I think what I'll do is I'll just rename this to input world velocity. Just so I remembered, like, not to add it on in local, in rig space or anything, just to add it on in world space. We could get rid of that print. Oh, don't delete forward solve. Now where we'll go is the trigger legs. So instead of just adding on a value of 200, we need to do something more complicated. So I'll just try to explain through how that's going to work. So the position where a given foot should land, let's just pretend he's on a treadmill, right? So this is just him walking on the treadmill. And I like to think of a treadmill when I'm thinking of it in rig space, because it's just basically, from his point of view, the ground is moving. He's not moving. So we want him to reach forward and land somewhere like this on the treadmill. But we can't just say this distance, or 200, or whatever it may be. What we're going to do is we're going to say where will he be plus this offset when he lands. So when the foot lands, we know how long it's going to take to land. We've got that as a variable. We've got the end path time. So we know when he will land. So that's a case of when the character has moved, you know, let's say it takes him, I don't know, 0.2 seconds before he's going to land. So at any time we can just check how long it'll be until he lands, or the specific foot lands, I should say. So he's going to go to here or wherever. So let's say he starts there and he's going to go to here. But then from this position, we then want to project forward that 200 so he reaches in front. So, you know, when you're walking or stepping, you're reaching a foot in front of yourself and it lands in front of you. And then your body crosses over that. So we need to do a projection forward to where he'll be when he lands, and then project forward how far we want the foot to move. And that will also be slightly based on the velocity. So if he's moving really slowly, he doesn't actually have to take these 200 unit length steps. He can just take some small steps. So we'll just try to implement that. So we're going to take the current position of the leg. We can just treat this as the legs rather than projecting the whole character forward. We'll take the leg position. So we've got the position that the leg is currently in. And because we want to add on a world space value, let's just take this value. So remember, this is just from the rig element key. So get transform of the current foot. We're just going to do to world to get it in world space. Then after this, we're just going to add on how far the character will move. So that's going to be the input world velocity. Scaled, so this is the equivalent of multiply. So for vector, you do scale if you just want to scale it by a float value. Scaled by how long it will be until he lands. So we get the end path time at our current index. And we want to know how long it is until this time. So we get our current cycle time. And basically, so we're expecting or hoping that this number is larger than this one. This one's in the future. It's not landed yet. We've just set this value here. So we're going to get this larger one, subtract the current time, and that's how long until it will land. So if this was 1 for some reason, it's got 1 whole second, then it would just be scaling this velocity by 1. And the velocity is movement, or distance over like every second. So how far it will move in 1 second. So if this number is less, like let's say it's 0.1, it'll be only the equivalent of how far it would move in a tenth of a second. So we just plug that in to scale the velocity, basically. So if we just do that, let's just do that for now. We'll plug that in. Yeah, so this is in world space. All of this is acting in world space. Then just do from world. And now we can just bang this into B. So we've got multiple axes of movement now. Oh dear. So I made a slight mistake there. Just a slight one. I've added it to the position of the bone. And this actually includes the position of the bone. So this is actually the only value we need. So to change it so it's connected to both of these, you can just control click on where it is and drag it to where you want it to be. So it's just from this from world goes into the to world. So actually, yeah, I could skip that, and it goes into the draw. Yeah, I mean this could be skipped entirely to be honest, but whatever. So his legs are just bobbing up and down in place, and the position that they're targeting when it moves is just their original position because we didn't add that offset yet. So they are moving, but they're all just moving to where the foot wants to be, so where the initial pause is telling it to be. So now let's just add on. Before we do the from world conversion, I can delete this add node now. Before we convert it back to rig space, we want to also use our velocity again. So we're going to add something extra on and plug that into B. We're going to get our input world velocity. And in its simplest form, let's just clamp this. So just drag out and do clamp length vector. Let's just say the maximum this value can be is 200. And then we plug the result into B. So now typically, because the character's moving at 600 units per second, this will always be higher than 200. And it's going to clamp it at our step range, how far we want it to step forward. If it's moving less than 200, it will make a smaller step. So that's actually not working. I don't know why. Okay, I figured out what's going wrong. So I'm going to clamp it again to 200. The reason is I just tested this. I paused the recording just to figure out what it was, but I was printing the input world velocity just to make sure that was actually working, because I wrongly assumed it was working because we added it on and it seemed like it was going to the current spot, but it would be going to the current spot anyway, so it wasn't projecting it forward at all. The reason is because I renamed the variable to input world velocity. It's killed it from our in the animation blueprint. So we just need to tick that again, use input world velocity. Because we changed the name of the variable, it basically lost the pin for that. So then once again, just right click on this, try get pawn owner, and then get velocity. And now you can see it's stepping ahead. And it's going too far, but it is working. So I'm just going to go into the character. Now that we've got like multi-directional movement, I'll just search for orient rotation to movement. Uncheck that. So now we can walk side to side. So that is working, even though it doesn't look like it. We're adding too much. We're adding 200 units on after it's projected where it'll move to. So all we're going to do is just change this number. I'll just do 50 and see what that looks like. So you can see that looks a lot more reasonable. It's stepping forward, predicting where the feet will land, and the legs always stay in range. Or mostly stay in range. I think sometimes like the back legs are going a bit elongated. So just to fix that slightly, where we've got this distance check, if it's greater than 200 units, I'm just going to lower that a little bit. So it's just going to be 150. And then, yeah, so now the legs at the back aren't getting stretched too far. So all is good for now, except the main issue we've got is the legs are just bobbing up and down in place. So now what we're going to do is make sure that it doesn't trigger the legs, even if we're doing this force leg trigger. So maybe that's a bad name because it's not technically forcing it, but we're going to do a check to make sure that the distance that the leg needs to actually travel is of a certain amount. So if it doesn't have to move at all, and it'll just stop it from bobbing up and down in place. Another simple way of doing this, and actually, yeah, okay, this is the way I'm going to do it. I've changed my mind. So one thing you could have done the way I was going to suggest is in here, just check the distance that it would be moving. So like predict forward how far it would be and just check the difference between the two to decide whether we should trigger the legs. That's a little bit more complicated. A simpler way will just be if we go to our calculate outputs, this is where we're doing this ramp for the leg height. So the target maximum we've got to 100. Instead, what I'll do is I'll just get the input world velocity. Doesn't matter that this is a world value. We're just going to do length of the vector. And basically, let's just do a remap. So remap this to a value of, okay, so let's say his max walk speed is 600, or his run speed, whatever you want to think of. And if it's 600, we'll just keep the 100, because I think that's not too far off. I think I'll increase it a little bit just to see what that looks like. So we'll do target maximum 150. So if the input is 600, so this is a 600 unit length vector, it will output 100. And we're going to plug that into here for the target maximum. Whereas if the world velocity is 0, the height it's adding is 0. So all these legs are actually triggering, but you're just not seeing them because they're not, they're not visibly moving up and down. So now he's stood in place until I start moving, then his legs start going. And another way that I sometimes think makes more sense, because I'll try to just explain what the issue is that we're trying to improve there. So all looks pretty good, but if he's only slightly moving, or it kind of comes to 0 velocity and then his legs readjust, they'll just slide into place. So rather than basing it on the current velocity, what I'm going to base it on is the distance that they need to cover. So rather than it being this input world velocity, I'm going to take the difference between these two. So that's just to remind you, because this was a while ago. The locked position is where we set off from. The target is where we land. So I'm just going to copy these nodes, paste them down here, get the distance between the two. So they just drop down the transform and get the translation. Get distance between these two vectors. And then we'll remap this instead of the velocity. So sorry for the time waste there, but yeah. So I'm not too sure what numbers these will actually be. I think I'm just going to print the distance. And that'll give us some idea of what numbers to expect. So the numbers are around 300. And we I liked the way that it looked with how far the legs reach forward and so on. So I'll say something like 350 just as the maximum. Get rid of the print node. So we'll map this between a value of 0 to 350. Gives us an output height of 0 to 150. And then I'll clamp it just in case anything crazy happens. And now what you'll see is it's virtually the same as it was before when moving. But if I stop moving, the legs will reposition, but they'll actually lift up to reposition. And you could tweak the values just because I think the lifting may be a bit high when it repositions, and they should just be a bit more subtle, but you can tweak that if you want. So you could just change the source minimum would probably help. So if you did say 100, then if it's less than 100, it will actually not lift at all. So that's maybe not enough. 20. Yeah, so now you can see that when the legs lift to reposition, they've got a smaller lift to them. And when it's walking, they're just high as they were before. It's a bit too high, it's that. So I'll chill out on this value. Just go back to 100. That's the maximum. Yeah, okay, so we've got him procedurally walking, and you can re-enable the orient rotation to movement if you want. Or you can make the character, what is it? Use controller desired rotation, so on the movement component, and then it'll be following, that's not it. I need to turn off orient rotation to movement and then use control desired rotation. So I can turn around with the mouse now, but I can also strafe. So it's looking decent. I think sometimes the legs might stretch a bit too far. I'm not going to worry too much about it. You can play around with these values and so on. So I think next is just to make it look better than it does. So currently the body's like locked in place. There's no movement of the body, so we'll add some movement of the body. We'll probably rotate the body or something like that. We'll just figure out some things to make it more interesting. And then I'll swap it over from this blockout version to the the higher poly sculpted version. And then we can see how things really look. So now comes the fun part where we're going to make the body movement more interesting. Then I'll lightly tweak a few settings, improve other things where we see fit. What I'll be doing is, so we've got this set final leg IK at the very end of the chain. And what this does is it's getting the current, well, it's actually getting the control. We don't need to get the control. Let's just do get transform of the pelvis. And bang that into the pelvis effector. That shouldn't change anything. Everything's still the same. But because we're using the pelvis now as the bone, if we do any modification to the pelvis position or rotation or anything before the set final IK, that will be included. So it'll just keep the original position that we've modified it to. And we've already calculated the position of the legs. So any movement we do, the legs are still going to go to where we've set them to do because we've already done the calculate output section. So here, I'm going to make a new function which will be called pelvis movement. And I'll just call that. So pelvis movement, then into set final leg IK. I think the first thing I'll do is I'll make it so that the body goes lower whilst he's moving. So when it's stationary, it can just be in this place chilling, and then maybe goes lower whilst moving, or the faster it moves. Maybe I'll do the opposite. Who knows? We'll see. The way I'll do that is I'll get the transform of the pelvis, so the current transform. We'll also do a set transform. Connect that in. Drop down the item, set that to pelvis. Drop down this transform. Well, I'll first plug the transform in so it makes that a transform input. Just plug the rotation in directly for now. Translation, drag out, add, pop that in. Let's get our input world velocity. What should we do with this? I'll take the length of it and then remap this to a Z height offset. So remap from 0 to 600, I think, is the character move speed. Obviously, if you're changing, the character move speed, you'll have to change these values. And if you've got something that's more dynamic, where it could be various speeds, or maybe you've scaled up the character, so one is actually moving like 6,000 units a second because it's a huge one, you might want to make these numbers dynamic. And you could do something like checking the size of the character or something to scale these values up, or whatever you want. So if it's 0, we'll just output 0, so we don't change the Z, and I'll plug that into Z. I'm going to clamp this because this could go wild. But if it's 600, let's just reduce the height of the pelvis by 100 units. So now what we should see is his body goes lower when it's walking. It's obviously a bit too low there. I don't know if this is the way around that we'd want it to be. I could go and look at what spiders look like. I'll just try the opposite. So we'll just say it's minus 60 unless it's moving when it goes back to the 0. I think I prefer it this way around. So I'll do 0 and then minus 30. But we don't want it to look robotic. So this is just doing a direct mapping of the velocity to a speed where it will just go zoop, 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 zoop. And, if he suddenly stops moving with his velocity, it'll just snap to the new, 0 equivalent or output. So what we'll do, after we get this float value, we can do a spring interp node. And this, I can't remember if I've used this before in this tutorial, but this just takes an input value and it tries to reach whatever this input is. So this is the target. And internally, this is keeping track of what the previous value that passed through it was. So rather than us having to create new variables to, to store something like previous Z offset or something like that, this is kind of doing it internally. So it knows what the value was last, it'll set it to that, and then it'll try to interpolate it towards the new value based on the strength and the critical damping. So the strength is self-explanatory. It's how strongly it will move towards the target. Critical damping, if this is a number less than 1, it will wobble into place, so it'll overshoot and then undershoot and then so on, and kind of double into place. Set that to 0.6, maybe leave strength at 4, see what that looks like. So that doesn't look good. I'm going to turn the strength down so it's a lot slower, maybe even turn that down. So you can see it just settles into place a little bit there at the end. And I don't mind how that looks. I think that's okay. I'll try a lower strength value, 0.5. It just settles a lot slower. I think the height change is too drastic. I'll just go to negative 15. Maybe lower the damping even more. I'm not going for realism here, by the way. I just want it to look cool. I'll leave that for now. Also, I think we'll do something similar for the rotation. So when he's walking forward, let's just rotate for now. We'll rotate his pelvis forward, I guess, or angle it down based on how fast he's moving. So for the rotation, we don't want to deal with quaternions. I'm not sure there's much you can actually do to modify them other than multiplying a quaternion by another one and so on. The easier way is to just do 2 Euler. So it's 2 an Euler angle, which is an XYZ value. And you're probably more familiar with this, especially if you're doing blueprint things. And then the rotation that we actually, when we plug it into the set transform, we want it to be a from Euler, so we just convert it back to a quaternion. If we just plug these numbers in directly, everything will be just the same as it was. But we want to modify one of these so it angles up and down when based on the speed of the character. So let's just see which axis that is. So it seems to be the x-axis. So if I plug in values for x, you see it's rotating in the direction, the axis that we want. So I'll just do x plus some value, and let's see if it should be positive or negative. So to lean down, yeah, so we want negative numbers for him to lean forwards like that. So the faster he's going, the more he's going to lean forward like that. Same as we did before, input world velocity, then we're going to remap it, and we'll use a spring interp. So I'll literally just copy all of those nodes and then just tweak values. I'm going to plug the result into there. I'll say -20 because that seemed to be a decent maximum. This should all be fine. Let's just tweak this value a little bit. 6.7. That's an accent. But... Right, so he's leaning a lot, much too far there, but then it kind of wobbles back into place. So I'll just make this subtle, so it's like 5, let's say. 0.6 for the damping, why not? Yeah, so it just makes it a little bit more dynamic, so it doesn't look like the body's totally static. You can see it just leans down, and also it's still going lower. I'll reduce the strength on the rotation, 0.4. See what that's like. Yeah, that's fine. I think what I'm going to do is make it so that based on the positions of the legs, the current position, we offset the pelvis like in the XY, so not the up and down, but so we'll move towards some legs. I'm not sure what we should do that based on, maybe the height of the legs, or we could do it based on which ones are grounded, so it moves more towards the grounded ones and favors those. I think for now, firstly, I'm just going to add some randomization to the position just so it doesn't just stay static and it's kind of wobbling around a bit. That might be enough actually, and we don't need to do anything else. But so on this add for the position, I'll just do a separate one. So I'll just add another vector to it rather than bundle it into this, because then we have to combine the z separately. We can right click and do noise. Plug the result into B. Drop down these. So let's just do 100 for the maximum for now. And you can see what's happening. It's sort of moving the character. It's moving in all axes here. Because it's 0 to 100, it's always going to be forcing it in the positive direction. So if you look at these axes at the bottom left, it's always going to be going in either that way, or up. It'll never go the opposite. So if we set the minimum to something negative, like -100, then it'll be anywhere in, it can go up and to the left or back and to the right and so on. This is too exaggerated. It's moving to the point where, the legs are getting too stretched and so on. But I'll just change the speed up so we can see how far it's actually moving, like the sort of range it's in. Yeah, so I'm just going to scale this down. So we'll do -20, 20. It seems to only be going in this diagonal, and I think that's because the speeds are all identical. So if we just did like 2.2 on this axis, 1.5 on this one, 0.5 for that one, you'll see that it's moving more erratically. It's not just going in one direction where it's kind of in sync, where all the movements are in sync. So what was happening before is because they were all in sync, it was basically whenever it was going higher on the y-axis, it was also going higher on the z-axis. So it was only going like in this diagonal. But now you can see that it's moving in all directions. Now let's chill it out on the speeds. So we still want them to be offset like this, but I think what I'll do is I'll take our input world velocity and we'll remap it so that the speed that he's wobbling around changes based on how fast he's moving. So for the first speed for X, 0 to 600 is movement speed. Let's use a value of 0. Well, maybe not 0. Let's start the minimum so he still has some movement. So it's 0.2, so it'll look like this. Except we're going to have them all slightly offset. Bang that into X, make another remap node, put it into Y, and I'll just change the... Oops, I don't want target maximum at -15. I want that to be something like... I'll try 1.5, so that the maximum it can do is 1.5 speed on this. This one I'll do a different number, so 1.2. The target minimum I'll tweak as well to 0.3. Then another remap node for the Z value. I'm just randomly choosing numbers basically. And then the maximum speed that can be, I think I'll increase that, so we'll do a value of 3 for the maximum of that. So now you can see that when he's just chilling, he's got some idle movement. And then when he's moving, okay, if he's moving, he's bouncing around quite a lot. I would say too much. So I think probably the best way is just to tune down the actual value. So if you just do, so it's halved it. So from -10 to 10. Still got a bit of idle sway. Bobbing around. It's definitely too fast. So these target maximums I'm just going to change to whatever, 0.6, 0.75, 0.87. Maybe go from -15 to 15. And just play around with this. You can just figure out numbers that you like. So he's chilling, idling. Unlike an actual spider, a spider just stays pretty much stationary when it's just not moving, but whatever. Then it's moving. It's still too much. I'll go to -5 and 5, then it's very subtle. So that's okay as a starting point. Now what I'd like to do is make it so that when the character rotates, his body doesn't just, it's not just locked to the direction that you set it to, so it has a bit of delay to it, and we'll use a spring interp except for the rotation of the body. And if we just did a spring interp between this get transform and then what we're plugging into the set transform, it wouldn't make any difference because this rotation in rig space, remember this is rig space, the get transform, there's no movement in rig space because the character's always just facing that way. Whereas if we first convert it to world space, so we do 2 world here, then we do our spring interp, and then we do from world, and then just plug it back to where it was. The value that's passing through the spring interp is actually a world value. And each frame, that will actually change when the character's moving in the world. Whereas if we just did it without the world conversion, that value is not changing because in rig space it's not moving. So now we do the spring interp for a quaternion this time. Plug the result into the from world. And if I just set this value quite low, so a value of 1, you should see that when I turn around, it takes some time for the body to actually turn. And I don't like how the legs look when he turns. I think the best way to fix that would probably be to predict the rotation change as well. So like we're doing when it steps forward, we're predicting the velocity change, but when it rotates, you can see his legs kind of tapping down. If we predicted the rotation change, it would sort of over-predict and it wouldn't have to update as often and step quite as fast. But I'm probably won't get to that. Okay, so his body's slowed down on its rotation, but let's just increase the strength but decrease the critical damping, so it should kind of wobble a bit. So okay, just, I don't know. I'll just try it with a low strength but higher critical damping. So when he rotates, he wobbles back into place. That's okay. Let's make this tail thing, well, this abdomen, I guess it is, wobble as well. So it's basically the same as this, except we're kind of doing this to set the transform of the pelvis, which connects, you know, it has everything involved. So that's going to move this as well. But then separately after this, we'll tell this abdomen piece, and I'll just check what the bone name, did I call it abdomen? I did, yeah. This one is going to have its rotation delayed as well. So it's always going to try and reach this position where it's directly behind in its default spot, but it's going to be delayed because we're going to add a spring interping. And this already has a spring interp, so this will be delayed, and then this will be delayed after that's delayed. So it's kind of like doubly delayed. So we just do a set transform. For the abdomen, we're going to get transform, abdomen. Translation we're not going to change. We want that to always be, you know, connected where it should be at the correct position. We don't want to move bones around because that'll stretch things. But the rotation, once again, we do 2 world, then spring in. Oh, not spring IK. We'll do spring interp. I'll just copy this one. And from world, pop it in. Yep. And now we should see that this tail piece is sort of wobbling. Now that's too much and exaggerated, but it is what we wanted. And I think that should also be doing it for the up and down rotation. So if I just, whilst it's still a high, you know, an exaggerated value, I'll just make it so when he rotates, which, where's that? That's here. That it does like quite a dramatic one, and then you'll be able to see that the abdomen's delayed from that. So it's not totally clear, but you should see that it should be moving up and down separately, I think. It's not totally clear that it is doing, but yeah, whatever. I think it is. I'll just undo, so I'll go back to -5 on this rotation remap. So I'm going to turn the strength up, and this is for the abdomen one. Maybe the critical damping up, so it should be more aligned to its original position. So you just get that little bit of wobbly waviness to it. Now, one thing that I'm not a big fan of is this rotation. So if you look at the left side, the legs are just sort of hopping along if I rotate quite quickly. I think a way to fix that is where we've got this distal than is greater than 150. We can probably increase this because we are triggering the legs. So I'm going to go to a value of 300 and just see how that looks when we rotate. Yeah, so I think that looks a lot better when it's rotating. You can still see it's doing it in sequence rather than it being forced to. If you turn fast enough, it'll force it to, you know, the legs to move. But if it's moving at some reasonable rotation speed, it's still doing, you know, the 2 groupings of 4 legs moving in sync. So I definitely prefer how that looks. We can also tweak some of the values for how fast the legs will move. So in trigger legs, we're doing, this is where a new leg gets triggered. We're doing the circle time plus 0.25. So what you could do is you could increase the circle time based on the movement speed, or you could change this number. So I'm going to do 0.125 just to see what that looks like. And now the legs should transition faster. So that looks a bit artificial and weird, but kind of creepy. Let's try a lower value, so we'll do 0.45. And now they'll be quite slow and floaty looking. Don't like that. That looks shit. I'll just do 0.2, see if that's any good. And a lot of this is just going to be testing values to see what you think looks decent. Yeah, I think maybe how we had it before was the best. So I'll do 0.28. Yeah, I think that looks fine. What's that little bug in the sky there? Ah, okay. Right, next will be, I think what we'll do is to make the body have a bit more motion to it. I think maybe I'm going to do the spring intert on its position as well. So the same as we're doing for its rotation, I'll do a similar thing for its the actual location of it. So rather than using this translation here, just going directly into this add, we'll do the from to world, then a spring intert, then from world. And I'll try not to make that too exaggerated. I just want it to kind of lag behind. So when the character moves, it go, you know, relative to the character, his body would be going backwards because his legs are going forward. You know, he starts setting off forwards, but it just takes a while to catch up. So we do to world, from world, spring interp, result, pop there, and then this just goes to wherever it was going anyway. Turn the strength low to make sure it's working as we expect it to be. Yeah, so you can see his body's really lagging behind now. His legs carry on as they were, but then his body's kind of being forced back to the previous spot. We don't want it to be so exaggerated, so I'll do a strength of 6. Yeah, so it's not totally obvious, but it is sort of subtly wobbling the character around. And maybe I'll turn the damping down now that we got the strength about right. Yeah, it's not too noticeable with all the rest of the things going on, but I think that's what makes things look decent sometimes. Like if you just layer a lot of things together and it's not totally clear, like if it's really clear that one thing's controlled by another or the exact formula that something's using to move, it kind of starts to look a bit artificial. But when you've got a lot of things going on, so we've got the noise, the rotation, the delays, the position delay, you know, and so on, it starts to hide what's really going on and it looks a bit more organic. There's something else I want to try just to fix a small issue I've noticed. The third leg, his third leg, so on the left, not the third one down. If you notice that, it seems to do like a weird stretching thing. If I strafe, so you can see it kind of snaps into like a maximum range like there. It's just snapping. It's quite difficult to show, but yeah. So his third leg on the left seems to snap out of range, and I think it's just because it's a smaller leg that it's doing that. So we could just bring the leg in so it's targeting a closer spot, or I could improve the skeletal mesh, or there is actually a joint there, although you can't see it, and maybe extend that. I think what I'm going to try first, which might be useful. So what I'm going to try now is offsetting the pelvis position, not just based on the movement or the speed or where it was previously using this spring intert, but I'm going to take an average position of all of the legs and then target it towards the center of those for the X and Y, and maybe even the Z before we do any of the other modifications on top. And what that'll do is make it so the character's always sort of centered around the legs. So if one leg is, you know, up in the air, it'll slightly move him upwards, and if all the legs go up on one side, it'll, you know, he'll go up by like half of that amount, sort of thing. So we're just going to be offsetting the center of the character. To do that, we want to get the positions of all the legs as we're outputting them. So just get output transforms. I could do this in a loop. Probably a better way would be to do it as a function where you just loop through and do that. But I'm not going to do it that way. I'm just going to do at 0, 1, 2, 3, 4, 5, 6, 7, 8. I did an extra one there. It should just be 0 to 7. So 0, 1, 2, 3, 4, 5, 6. Okay, I didn't do an extra one. 7. So we get all of the output positions, and we need to just connect this so it knows what array to be using. And then we're going to get an average of all of these. So what you can do is array average, which will give you the average. I don't think you can do it for transforms, no. So we'll drag up from this and do make array. Okay, I think for some reason that doesn't work. Maybe, but then I should be able to plug. Yeah, so I'll just create the entries on this. Don't need them all to be like that. And then we're just going to plug each one of these elements in. The translations that I'm plugging in, obviously. And you can understand that if you're doing a centipede, that doing a loop would be the better option. So this should give us an average position of all of the feet, so where they're being output to. So just as a test, let's just use that position directly, and you'll see it goes to the ground because they're all, you know, the feet are all on the ground. I kind of liked how he landed then. That looked kind of cool. That did not. So because the legs are going up and down, it's causing the body to bob up and down. So I think I might just completely ignore the Z. But the X and Y position, it's keeping his body in that average position now. And we might tone this down and use it as an just like offset rather than absolute value, or blend it to the original or something. I think what I'll do first, I'll just take out the Z value because that's making it weird. So I'll just plug in the X and the Y. And the Z, we just want the original translation of the pelvis. And let's just see how that's looking. So now I think that's a bit more natural. It's not quite fixed the issue I wanted it to fix, but I do like the look of it. You can still see that those third legs down are getting into something. It's not too bad now. It's kind of somewhat helped. But I think that's too exaggerated how he's kind of wobbling. It's okay, but I think I'll just blend it between this array average and the original. So we get the original translation, do interpolate. I'll plug that into B just so it's cleaner. Take the average from here, and then just use the X and Y after we've interpolated. And now we can control how much. So if this is a value of 0, it'll be fully this wobbly one that's just the average of the legs. If the value's 1, it'll just be the original. So I'll do something in between, so 0.5. So we should still get some of that back and forth, but it's just not as exaggerated as it was before. I think overall we might want his pelvis to be lower down. I think he looks like he's too high up there. This is such a mess. So we're mapping it from 0 to -15. I'm going to try -15 to -25. Is it? Just make sure I'm doing the right thing. Yeah. No, maybe -30 to -45 or something. So now his default pelvis position is lower. And again, you can just do whatever you think looks best for that. The main thing that we're missing at the moment is that the legs are just, they're not dealing with terrain. And because we're on a flat ground, it's been fine. But we want the legs to step up onto things, and, you know, we want him to be able to walk up ramps and so on. So I'm just going to, you know, alt drag the floor. I'll just show you what it's currently looking like if we go up a ramp. You can see that the legs are just going into the floor there. And floating as well on the other side. It's quite an easy fix. We just do trace lines. You can do trace lines now in controlrig. It used to just be the sphere traces. Now you can do line traces, which is more useful. So I think I'll add that next. So to get the legs to actually meet the floor, when it's going on curved surfaces or uneven terrain and so on, what we need to do is add some traces. So when we do our trigger legs, this is where we're tying it where the world target transform is. Instead of just using that value directly, we're going to do a trace from above the character or above the legs to the spot where we want to land. And then we'll go further than that. We'll project it forward so it goes down into the ground. Because if it, like in this case, where if you look at the legs on the left-hand side, because the character's actually higher up, the ones on the left are floating. So we want to project further down so that the legs would still reach the, you know, find the floor. So at the moment, when we project after we've done this projecting forward based on the velocity and so on, we want to do a line trace. If you just right click, do line trace by trace channel. This is in rig space, so we just want to make sure we use rig space values. And handily, we've got this from world, so we've got it in rig space before we do this to world. So we can just do it in between these two. So it will trace from, this will be like the ideal kind of goal that it's going for, but we'll trace from some position above this. So let's just add a value of, and there's better ways of doing this where you could do it like between the foot and the leg, so it would reach walls and so on and act a bit, you know, maybe a bit more realistic in some situations. But for now, what I'm going to do is just a simple case where it's just doing a straight up and down trace. In the course, the controlrig for Unreal Engine course that I've got where it's a scorpion, we do more advanced traces where it kind of goes at an angle and so on. So it always tries to find the floor, even if there's not just a expected floor directly beneath, but if there's a wall behind to the side, or if it's on some like shorter platform, it will kind of reach down below and grab onto something and that kind of thing. That's a bit more of a complex setup, so I'm not going to go through that, but we'll add on a value to this position that it's trying to target and just raise it up in the air relative to the rig. So I'll just do plus 150, and that's the end of the start of the trace, sorry. The end of the trace is going to be the same position, except we add a negative value. So let's do negative 150. I don't know if these values are right. So that goes into the end. The hit location we want to use, but only if there's a hit. So if we drag out from this to world and do if there's a hit, then we use the hit location. Otherwise, let's just use the location that we were using anyway. So we'll just plug that into false. So from world goes into the false. Now you should see that the legs, everything looks normal on ground, but when it goes up, you can see that the legs are raising up now onto the, yeah, so they lost it a little bit then. But you can see that it's angled, you know, the ones on the left are low, the ones on the right are high. The reason it's not quite working like that is because I don't think, well, firstly, we're not projecting velocity, because the Z velocity, because we're just doing that input world velocity rather than calculating in controlrig. So that's one of the reasons that I don't like to pass in a world velocity rather than calculating it. Another reason, by the way, whilst I'm here on this little tangent, for testing things, I like to just drag the character in, simulate, and just drag them around in the world. But you'll see that, I mean, it's mostly working, but there's no velocity in this case. It doesn't calculate the velocity when you're just moving the character around like that for whatever reason. So it's not predicting forward, so it looks weird. Anyway, back on track. The easiest fix for this, I'm just going to increase this to 350 and negative 350. So it's basically drawing quite large lines, so it's almost bound to find the floor now. I can delete this dude. So now it's crawling up, the legs are landing on the floor up there. And it's always finding the floor going down as well. Now that we've got some height going on when he walks on uneven terrain, I am actually going to make the offset of the pelvis related to the height. So before we're just doing the X and Y locations, or the average, but now what I'll do is in pelvis movement, when we're taking this average, I am actually going to use the Z value. I think what I'll do, I'll just first plug the Z value in directly. Now that it's blended between this and the original, it won't be too bad. So it's not directly grounded, it's just halfway between. And I kind of like how it looks when it's low to the ground. But you can see it's bobbing up and down quite weirdly. Instead, what I'll do is take this Z value and spring into just the Z value to smooth the Z out, so it won't be bobbing around quite as jerkily. So you can still see it's going up and down when the legs are moving, but it's not doing anything too crazy. And when it's going up a ramp or whatever, if some legs are higher, it'll be, or if all the legs are higher or whatever, it'll be moving the body up and down as well, which helps. I think that's making the pelvis a bit too low. I could change this, so it's, what you could do is you could calculate all of this and then compare it, so subtract it with the initial positions of all the feet, to find where like the center actually is, and then you can use it as an offset. So rather than just using the absolute position, but I'm not going to do that. Here I'm offsetting the Z value of the pelvis translation. I'm just going to reduce these values now because it's already lowered because of what we were doing up there. So I think that looks decent. I'll keep those values. And just to show you in case you want to copy it exactly, -15 to -25 from the velocity map. So that's decent. We could stop there. But there is one thing that I think would be useful. When he's going up a slope, his body is perfectly flat. And I think what we'd rather him do is angle his body based on the surface normal that's below him. So if he's walking on a surface like this, or he's walking in this direction, he'd be leaning back, sort of walking up it, rather than just facing straight forward. And the opposite for going downwards. So if he's going down, he'd be leaning down towards the floor. You get what I mean. So I think I'll try doing that next. So to angle based on a surface, I see people doing this in the most complex ways, and I think I used to do it in this way because I didn't know a better way, but it's quite a simple way to do it. So what we'll do in our pelvis movement function, for now, we'll just skip out all this that we've been doing. So we just won't use that just for testing. So just so it doesn't complicate matters, we'll just try and rotate the pelvis based on the floor underneath. So first we're going to need a trace. So just do trace. You could do a sphere trace or a line trace. I'm just going to use a line trace. I'll set the values manually because it's just, you know, this 0, 0, 0 is just rig space center. So I'll just do some point somewhere above and then some point somewhere below. So let's just do a value of, I don't know, 400 above, and then it ends at -400 on the z-axis. So we're doing a trace straight down from above to below the character. If we hit the ground, we'll be getting this hit normal. And the hit normal is just telling you the direction that the ground's facing. So in this case, it'd just be pointing straight up. So it'd be a value of 0, 0, 1. So x, y, z, 0, 0, 1. It's just facing straight up. So it's like a 1 unit vector pointing upwards. The way I like to do it is just to say, what's the difference between the current upwards direction? So that's just 0, 0, 1, pointing up. Or any number, you can do 0, 0, 10,000, whatever. What's the angle between that and whatever the floor is? So if the floor isn't 0, 0, 1 and it's, you know, slightly pointing down or tilting to the side or whatever it is, then what's the difference between straight up and that angle of the floor? And then you just rotate the character or whatever bone by that angle. So this works for the whole character or for feet. So if you want in the, like, you know, if you have a character that actually has feet, you want the feet to land to the floor or whatever, you just take the normal position that they'd be in. You say, what's the difference between the straight up direction and the straight up from the floor direction? And then you just apply that offset. Simple. The way we'll do it is we can do from 2 vectors. So this takes 2 vectors and it creates a quaternion that represents the shortest rotation between the 2 vectors, as the tooltip tells you. So one of these vectors is going to just be straight up. So I'll just type in 0, 0, 1 to be straight up because that's how we want it to be in normal situations. And then the floor angle is going to be this hit normal, presuming there is a hit. If there isn't, I think it'll be fine. We don't need to do this check, but so the hit normal is going to be B. So it's creating an angle between these 2 vectors, so straight up compared to whatever the floor direction is. And it gives us this quaternion. So that you can think of this as an offset between normal and the floor. So all we have to do is, let's just do a separate set transform just while we're setting this up. So just pop that in there and make sure you link to the return node. We'll do a get transform just to get the original pelvis position, translation and rotation. So pop those 2 in, set this to pelvis. And he's back to normal. What we want to do is just take this rotation, which is the quaternion, and we want to combine it with this one. Now the order of this matters. and it can be a little bit difficult to remember, and I'm not going to go deep into the maths on it, but I'll try and give you a good way to think of it or understand it. So if we take this one and we do multiply and plug this one in, this is combining the two. So it's not multiplying in the typical sense where if you had two float values or just two numbers and you multiplied them together. It's a bit more complicated than that behind the scenes. But the way you can think of it is it's this applied to this. So whatever this is applied to this. So for example, if you were rotating a bone by 90 degrees, you just want to turn the character by 90. This would be 0, 0, 90. Or if this was an Euler angle, it'd be 0, 0, 90, but then it's to a quaternion. It'd be, a 90 degree offset applied to the character. Whereas if you do it in the other order and you do the character's rotation, that would be the character's rotation applied to the 90 degrees, which is different. A way to think of it is maybe if you think about the difference between walking forwards and turning 90 degrees at the end, or turning 90 degrees and then walking forwards, you'll end up in two completely different places. The order it matters for those. There is some math term for that where it's, where you can't swap. I don't know what it is, right? Anyway, so we just pop this in. So we apply this rotation change, the difference between the hit normal and just straight up, and we apply it to the bond, the transform rotation. So now you can see that when he's on this slant, okay, so because I spawned on it, the camera's gone a bit peculiar. No, he hasn't. So what you should see now is everything's normal when he's just on flat ground, and now it snaps to pointing straight up, and also make sure that it's working sideways. So like it's it's rolling, tilting the character that way. Still works going downwards and everything. So everything just works just with those few nodes. And other people I see doing tutorials do it with like the aim node. So there's some aim math nodes and so on. I found that a lot more difficult. You have to set all these, primary axis, secondary axis, all this kind of stuff. This way, I don't really know why you wouldn't do it this way, basically. So we've got that. We're going to smooth it out. So as you see, it just instantly snaps based on the hit normal result. So as soon as it crosses that boundary, it just snaps to the position. We know how to fix that. We just use a spring interp. But let's just involve the rest of our stuff first. So it's a little bit messy, but this is after we've done all these calculations that we did to offset the rotation. And so, well, this one's for the rotation. So all this section here is related to the rotation. So let's just do it to this number. So we just take this number and plug that into the B. So it's just changing it, after all of whatever happens here, it's then doing this rotation based on the hit normal. And then we can just use that as the rotation. And we just connect the execution path back to where it was and make sure that goes to the return. So everything's as it was, but now it should be snapping to the new rotation when we get to there. So far so good. Now we just need to make it interpolate so it's not snappy like that. I'll just bring this down. We can get rid of this set transform. We need those. Again, you can select things, collapse to functions, make things more organized. In the interest of time, I'm not doing that. We don't need that get anymore. So what I'll smooth is not this, because we don't want to smooth the whole thing, any rotation that happens. We just want to smooth the difference between like the change in the hit normal. So we don't even need to do this in world space or any conversion. We just do a spring interp after this from two vectors. So do a spring interp of a quaternion. I'll give it a strength of 1, maybe 0.9 for the damping. Why not? And let's see what we get now. So now you can see it's a much smoother transition when it changes the rotation. You barely notice it. And if you want to take this a step further, what you could do is you could do multiple traces and take the average of the hit normals. So for example, you could do one that's in front, one that's behind, and so it kind of gradually ramps up, and so you have all 3 traces and it's taking the average. Or you could do something more complicated, like kind of taking the plane that's created or a triangle that's created by 3 of the feet or something like that, and using that as the normal rather than just doing the trace. This is fine in this case. The only exception would be if you had like some really small things that are angled weird, and then like as he walked over him, the hit would be touching the angled sharp thing, and he'd twist his body, when really just on flat ground you probably wouldn't want him to. That's not a huge issue, but yeah, it's just something to look out for, and a way that you could improve it a little bit further. So I think what we've got now is pretty good. I'm not sure what else to do. I think it might be time to just switch it over to the character, make sure everything's working on the actual character, and call it a day. So now this is how it's looking applied to the actual character mesh, the sculpted version of the character. And I've made some basic landscape just to test it, how it looks when it's walking around on the landscape. And you'll have seen this in the intro as well. But yeah, hopefully you've got something that looks similar to this. The shadows don't look great on the character because of the hair. You can just turn that off if you don't want to use it, but that's what I decided to go with. I did, when I switched to the sculpted version of the character, I did fix one of the legs. So the third leg down has more length to it now, and it's got a bit of a bend in it, and so it doesn't do the weird snapping when it goes side to side. That's the only change I made. Other than that, this is basically well, it is exactly the same as the blockout in terms of the skeleton and the mesh and everything. It's just that this one looks different, and that little leg fix. Yeah, but you can get this in the description. This, I think I'll have this as a paid one, and then the blockout version's a free one. And if anyone's interested in how to make characters like this, I'm not good at 3D modeling. I'm not great at it, but I think I've got a good workflow that just for prototyping things and making characters quickly. So if you're interested in that, let me know in the comments. Hopefully you've liked the video if you've made it this far. I assume most people will have dropped out by now because it's over 2 hours. Yikes. But yeah, if you like the video and you want to see more like this, just let me know. Remember to subscribe, hit the bell thing, whatever that does. Like it, share it, rewatch it a few times. I don't know. Yeah. Thanks for watching. Watch my other videos as well while you're there, and buy my courses, of course. Bye bye.